Hello. Okay. Today we'll be doing a proof of the Bolzano-Weirstrass theorem. It is a classic theorem in real analysis and probably other places. And it says that every bounded sequence, so every bounded sequence has a convergent subsequence. All right. And so let's prove it. So to prove this, we'll assume we'll let a sub n be a bounded sequence. All right. Okay. So by definition, there exists some m, capital M, such that the absolute value of a sub n is always less than or equal to m. So what does this actually look like? Let's look. So we have the number line here, the real number line. All right, right there. Here's m, here's negative m, so somewhere in the middle we'll just call 0 there. And then let's see, red, blue seems good. And now here we have a whole bunch of points in our sequence. So these are all, so our sequence is just bouncing around the real number line. All right, and so a sub n is those blue dots there. All right, so let's bisect this these intervals first, because we're trying to show that we can find a convergent subsequence. And so to do this, we will first bisect the interval negative m to m, okay, into negative m to 0 and 0 to m. Now, there are an infinite number of terms in our sequence. And so when we split this in half, one side of one of these intervals must have an infinite number of terms. So choose the interval with an infinite number of terms and call it I sub 1. All right, and now choose a sub n sub 1 such that a sub n sub 1 is in I sub 1. Easy enough. Okay, so let's look at this over here. I drew more dots on this right half, so we'll call this right half I sub 1. And now we chose some beep a sub n sub 1 in I sub 1. Perfect. All right, now let's continue. Now bisect I sub 1 into two intervals of even length and choose I sub 2 to be the interval with an infinite number of terms. Infinite number of terms. Okay, because there are an infinite number, there are an infinite number of terms in I sub 2, we can find some n sub 2 greater than n sub 1. And then just let a sub n sub 2 be in I sub 2. I think I could have worded that a little bit better. Let's see. Because we can find some a sub n sub 2. Oh wow, that's a big eraser. I didn't expect that eraser to be so freaking ginormous. Okay, let's see. We can find sub a sub n sub, because there are. We can find some a sub n sub 2 such that a sub n sub 2 is in I sub 2, and n sub 2 is, oh, that's just n2, and sub 2 is greater than n sub 1. Okay, and this will be important. All right, so now, in general, well, let me actually draw this out first. So we've bisected I sub 1 into two parts. Oh my word, everything's going wrong. Let's say we've bisected it into two parts. Call this I sub 2. And now we've chosen some a sub n sub 2 in here, such that n sub 2 greater than n sub 1. Okay. Okay, so in general, construct I sub k by taking half of I sub k minus 1 by taking a half of I sub k minus 1 with an infinite number of points and not an infinite number of points, an infinite number of terms, of a sub n, and choosing n sub k greater than n sub k minus 1, greater than greater than n sub 2, greater than n sub 1, so that n sub k, a sub n sub k, a sub n sub k is n I sub k. Okay. Now, we want to show that a sub n sub k is a convergent subsequence. All right, first, we need to find a candidate for the limit. I mean, we have a subsequence, and it seems like, I don't know, it might converge, it might not. Let's find something that it could converge to. Notice we have I sub 1, we have like this I sub 2, we have this infinite nesting of intervals because I sub 2 is solely contained in I sub 1, and, I sub 3, if I drew it in here, I sub 4, 5, 6, they get a little hard to draw after a while, but they're all fully nested into each other, nested. That's important. Because we have a theorem about nested intervals. By the nested interval property, I don't want to write that all out. Nested interval property. There exists at least one point we'll call it x in the intersection of every I sub k. In the infinite intersection of I sub k. Okay. This seems like a good candidate for a limit. So let's show that the sequence a sub n sub k converges to x. That's a very phi x, but it's okay. All right. And to do this, classic epsilon n proof. So let's let epsilon be greater than 0. Okay. And so by construction, the length of I sub k is m times 1/2 to the k minus 1. And this is because, of course, we're dividing to create the interval I sub k, we are dividing m in half k minus 1 times. All right? And this converges to 0. Dividing something by 2 over and over and over again converges to 0. So let's see. Choose n such that k greater than n implies that the length of I sub k is less than epsilon. All right. Let's see. We know x is in I sub k, and a sub n sub k is in I sub k. Thus, we have a sub n sub k minus x is less than epsilon, because the length of I sub k is less than epsilon. So taking 2 points inside of them and finding the distance between them can only be less than epsilon, which is what we wanted to show. This is showing that the subsequence a sub n sub k converges to x. So let's draw a little box and be happy. All right.